So let's start. Let's welcome our first speaker, Adam. He is software development engineer, public speaker, writer, blogger, and scientist. Wow. He will be presenting on the missing chapter in your CI playbook, database guardrails. In his talk, Adam will share his insights on how to ensure that ORM-generated SQL queries are safe to run in production. Hi, Adam. Please start.
Hey, everyone. Thank you for introducing me. I'll just now capture the screen and start sharing my slides. Hope you can see that all. And hello, everyone. I'm a software engineer working with Mattis currently, and we wanted to share a little bit of expertise, how to construct the CI/CD pipeline, how to introduce database guardrails, and how to improve our deployment process to make sure that all we do is actually going to work well in production. Because as we know from our experience, as we know from empiria, from practice, it's pretty often the case that when we develop something, we do not necessarily know whether it's going to scale out well, work well in production once we deploy there. So what we want to do is we would like to make sure that whatever we do is actually going to be very solid and won't fail once we deploy on Friday afternoon, right? So in the next 40 minutes, what we are going to do is we are going to see which things may go wrong and how to prevent that, how to prevent bad code from reaching production, and how to make sure that our CI/CD pipeline and everything around our software life cycle is of top-notch quality. So the very first thing we want to stress is we always, as software engineers, we need to be proactive and we need to push to the left. We can't let ourselves just deploy the application to production without making sure, without testing whether it works properly, whether it works well. We need to test our application. We need to make sure that whatever we develop is of a high quality. And we need to do that as early as possible. We can't wait with these tests until load tests. We can't wait until the very end of our pipeline. What we need to do is we need to make sure that everything works well right when we are typing the code, right when we are implementing the app code of our application, right? So what we are going to do is we want to push these checks, automated tests, QA, whatever else, to the left in our pipeline to happen as early as possible. The other thing we need to do is things will go wrong anyway. No matter how hard we work on deploying things, how hard we work on making sure that whatever we deploy is of the highest possible quality, things will break in production. Why? Because of different data, because of different data distribution, data volume, because of different traffic coming over weekend compared to weekdays. So whenever something goes wrong, we need to find the root cause automatically. We need to have as much details as possible to identify where the problem is without learning all about the ecosystem, right? What we want to do is we want to have everything at our hands, everything about the database, about our application, about configuration, running config, scalability, environment variables, whatnot. We want to have all of that combined together so that we can identify and find the root cause as early as possible and us automatically as possible. This is a must-have for every business, not for big companies, Fortune 500 enterprises, nothing like this. This is for small companies, for startups. This is for big companies as well. This is must-have for us as software engineers today. So before actually moving on, how do we actually make sure that whatever we do is going to work well in production, right? Everyone tells us, hey, we need to deploy often. We need to deploy continuously every single day. How do we make sure that things that we deploy are going to work well? But more importantly, how can we figure out what can even go wrong, right? And there are various areas of in our software engineering that may go wrong. Starting with the deployment may break, right? We have multiple platforms, typically Windows, Linux, ZOS. We may have mobile devices, IoT devices. We have hardware platforms, software platforms. Things differ between those. Sure, we can test some of the things locally. We can test things in our local staging environments, etc., etc. But ultimately, what happens is there are differences between our environment where we implement stuff and the environment to which we deploy. Differences like even very silly things, like for instance, the directory separator, like slash versus backslash, right? New line ending or whatever. But even bigger differences, for instance, how operations are implemented behind the scenes. For instance, Git is very bad on Windows because Git uses completely different IO operations that are unfortunately not very well optimized on Windows, or at least used to be not very well optimized, but they were very fast in Linux. So those things may differ between our platforms. Not to mention things like permissions, like IAM roles, like things in our cloud environments, like on-prem environments, connection strings, environment variables, all the other stuff that needs to be deployed successfully to production for our application to work. It's pretty often the case that, hey, we deploy something, it worked well, like flawlessly in staging, but once we deployed to production, we learned that, hey, we didn't deploy like environment variables, right? Or we didn't deploy all the settings for Docker containers, right? We don't have proper like memory settings, CPU settings, and other stuff, right? These things may just break when deploying to production, and we need to identify and test all of them before moving on. That's first area. The other area we have is our code may break. As simple as that, our code may contain bugs that were just not captured during like system testing. But also our code may have some inherent like dependencies on the locale, on the environment that we are working in. For instance, already mentioned like line endings and other stuff, right? But those are the things that we are pretty often used to. We kind of know how to identify them, how to test them, especially if we can mirror production environment in our like dev staging environment. So those things are cool. However, our code may face completely different conditions under which it is running. For instance, different traffic, different data distribution. We tested our stuff with like US database, but then we deploy to tiny country in Europe, and then we get completely different data traffic, which our code just cannot handle. We have this phenomena of like works on my machine, but once we deploy somewhere else, it just doesn't work and we have no idea why, right? We need to figure out how it goes. And finally, the very last thing is increased load and scalability. Like it is easy to test our application locally when we have like 10 rows in our database and everything is going to work well. But in production, we'll face completely different traffic that depends on like time of day, time of week. You have different peak hours depending on the business you're running. If you run like e-commerce application, you'll probably get much more traffic like near Christmas or near Halloween, right? If you're running like a ticketing system, then probably people will buy tickets like early in the morning or right after coming back from the office because of how they commute to work and come back home, right? We may get completely different traffic when we run like a streaming application for videos, because then people will most likely watch stuff like in the evening or during weekend, right? So this changes how we can test our application. If we are testing that only like at this very specific hours, the same time every week, then we may miss different traffic distribution, different traffic load, traffic coming from different countries, from different segments of our users. All those things are very hard to test like in our pipeline, just because, well, we would basically need to run another production. And running another production is like very hard from technical standpoint, very expensive, and most importantly, it takes time. So we see that for like 3 different areas of how we deal or what can go wrong with our application. And whenever we think about, okay, how do I make sure that whatever I deploy is going to work well in production, they tell us CI/CD is the answer. I know CI/CD, I know how to do the stuff, right? Well, CI/CD stands for 3 different things. First concept is continuous integration, CI for sure. What we want to do is we want to merge our branches into main branch. We want to compile the application, run all automated tests, unit tests, integration tests, you name it, run them locally to make sure that what we built is actually going to work well. We have all the dependencies, we have all the libraries in place, code is there, and basically code works on the critical paths that we identified. Next thing we want to do is continuous delivery, CD for sure. What we want to do is we take the package that we just built, we've just tested, we deploy it to all the non-production environments just to keep everything in sync. Our developer environments, QA environments, staging, pre-production environments, all of them should be running exactly the same code, should run exactly the same tests, so we can see how it works and we can be consistent across our company, right? But then we have continuous deployment. Continuous deployment is when we take the package and push it to production automatically, right? Technically, this is very straightforward. We just deploy to a yet another environment. However, there are various things around that that may make it much harder. Those things are, for instance, we probably don't want to deploy during peak hours, right? Deployment may take time. Even migrating the database may take like minutes or even hours. We have completely different traffic distribution. We have caches that may be flushed. Generally, tons of things we need to take into consideration when deploying automatically to production, and especially when we are talking about how do we make sure that our application is going to work well, right? So those are the things that we need to be aware of. And let's now dig a little bit deeper into what can actually go wrong when we are talking about like CI/CD pipeline and databases, right? So we will cover issues with databases, with ORMs, and the most important issue, which is lack of context when something goes wrong. So we'll go through these 3 different areas to see which things we may face, and later on we will see how to fix them and how to make sure that we do not make any silly issues. So the first thing is problems with databases, right? We use SQL databases, NoSQL databases. Generally, we have some data storage that is backing and powering our application, right? Whenever we talk about databases, we can group issues with them into like 3 high-level areas where things may go wrong. Very first thing is code changes, right? So we change our application code. We change the code, which in turn generates different SQL queries or different queries to our database. Those queries, because they are now different, they have completely different characteristics, right? They extract different data, access different tables, different columns, and obviously have different performance. So this is the very first thing. We typically test this area using unit tests. We make sure that what we generate is actually doing the right business logic, right? So this is kind of covered. The other thing which may go wrong or which may cause some issues is schema changes. Basically, running any schema migrations that we may have, adding new table, adding new column, changing column type, configuring indexes, changing view definitions, stored procedures, functions, you name it, and whatnot. And generally, those things that are very straightforward to test, because like if we screw up the schema migration in our application, then we immediately see what is wrong because like the column doesn't exist and we get weird errors from our database engine, right? But there are 2 different things that we typically miss when we're talking about testing. First thing is those migrations, they take time. Adding a new column type or a new column to a table may take like split second, but if we need to rewrite the column, then this may take like minutes or even hours in a heavy loaded and very occupied system. Same goes for adding indexes or rebuilding indexes. These things may take time and we just can't take that locally. Why? Because when we take things, test things locally, what happens is we have like 100 rows in our database. We have very scarce number of like entities that we could run against, or we could run against migrations, those against the data, right? So what we don't see is how this thing is going to work when we have plenty of data in our production database. So once we started the deployment, it may take way longer than we expected, and we won't catch that typically with our CI/CD. The next thing is query changes, how it executes. We are not talking here about the query text. We are not talking about changing the query that we run. No, we're talking about we have the same SQL statement that we run over and over again for days, weeks, or months. But now, because of different data volume, because different indexes, different configuration on tables, we get completely different execution plan. And effectively, the query works differently, works way slower, or extracts data in different way. Again, something that we won't spot when we are talking about testing environments, but something that would hit us the very first second we go to production. So let's see what can go wrong. For instance, talking about slow queries. This is actually an example from one of my production systems. So imagine that we have this big aggregate root. And what we want to do is we want to get the user entity, and this user entity has multiple tables tables that we would like to include, like details, pages, text, reports, whatever else. When we implement like an application code like this, what happens behind the scenes, our ORM will generate the select statement like this. So select with multiple joins, right? And this thingy resulted in, just for one aggregate root, resulted in getting around 300,000 rows. And ultimately, those 300,000 rows were returned to the ORM and then processed by the application by something like 25 seconds. The application code. Why is that the issue? Well, the issue started because we have these multiple joins, and because whenever we join rows, we join tables, what happens is we have many more things that basically exponentially increase the number of rows we get. So this results in 300,000 rows being delivered to the ORM, something we won't capture at all when testing things locally, when we have basically like 100 rows in our database, right? We won't see this exponential increase. We won't see those Cartesian products happening behind the scenes because we just don't have enough data. How can we fix that? Well, in order to fix that, at least in this case, the solution was to split this aggregate root into multiple different queries. So get all the components of this aggregate root like independently, effectively running multiple independent select statements to our database, and then combining all of that in the application code. Even though we were running many more SQL statements, all of that executed in like less than a second, in split second, just because we were getting much fewer rows to our application. So it's not as clear that, hey, the more the queries you have, the bigger the problem is. No, that's not the case. In this case, sending more queries was actually improving the performance, something we wouldn't catch in tests, right? Something that we would see only in the production. But the other thing with database and queries is queries can be equivalent, but have completely different performance characteristics. For instance, take this. I have boarding passes table with something like 8 million rows, and I sent two handcrafted, obviously, queries that do exactly the same. First query uses common table expression, kind of like a synonym for temporal table, in which I take the ticket number and I calculate a hash it twice using MD5. Right? Then what I do is I join these tables like this temporal tables 3 times and get the rows for very known like hash ID or hash number for this ticket number, right? And this thingy executes in 13 seconds, right? The other query that we can run is equivalent. This is exactly the same query returning the same data. The only difference is now it injects like this MD5 hashing 3 times in this where condition instead of preparing like this temporal table, which is CTE here. But this thingy runs in 8 seconds total, okay? So what we see here is you get the equivalent query. So your ORM, your library may generate either of these queries, and you can see that they will give you exactly the same result, but you will get completely different characteristics. Still, something that you won't spot easily with like unit tests because, hey, the result is the same. You get exactly the same output. However, if you have only 100 of rows in your database, you won't see the performance issues. To get the performance issues, you need to either go with big load tests, which are heavy, take much time, and are very expensive, or you deploy to production, and that's when you learn about that stuff, right? Again, same issue that we can't easily catch very early in our pipeline. Another thing is something I already mentioned, incompatible changes in schema, right? Adding a column, that might be a problem when you go with select star. It may cause like table rewriting, reorganization of the table, index rebuilding, just because you added new column that must be somewhere in the middle. And because you have like clustered index, you need to have rows ordered like on physical drive. So you need to rewrite whole table, right? Dropping a column, this is very dangerous because depending how you run the deployment or whether you have heterogeneous applications or not, you may get completely different errors than when you run things locally. Why? When you run things locally, you typically run things only like on single node. You do not scale out your application locally, right? But once you go to production, you may have multiple nodes running your application. Now, if you can do the deployment atomically, meaning that you can deploy a completely separate fleet on the side and then atomically swap like load balancer to hit the new fleet, then it's all good. But if you are replacing hosts one by one, then at some point you end up with thing that we call split blame. Half of your fleet is running with the new code, the other half of your fleet is not running the latest code, is running with the older version of the code, which means that, hey, you basically expect completely different schema in the database. If you do not have migrations that are backwards compatible, then you end up with issues that your old version of application will just simply fail. Similar case is when you have heterogeneous scenarios. So when you have multiple applications running against the same data store. So the other application may not have the schema updated yet, and you end up with issues because, hey, the column is not existing anymore, right? So this is the issue with schema migrations and other stuff that may actually break the applications like in place. The other problem with schema migrations is just the performance. Rewriting the table may take minutes or even hours. Do you want to take your application down just to deploy the latest version? And if you do want to take it down, maybe you need to take it down, then how do you make sure that your clients and your customers are not affected? How do you deploy this? Do you do it at night, etc.? Generally, various things that you need to be aware of and are very hard to be tested like in your local environment. Missing indexes, yet another case of database issues. Like whatever happens when it comes to performance, people tell you, hey, you should have an index. If you add an index, obviously your reading improves, you have selects running much faster, but at the same time, your updates are way slower because now you have multiple data structures to be updated. And the thing with indexes is when like a junior developer learns how to improve the database performance, that adding an index is a solution, what we end up with is too many indexes in our database. So we have way too many indexes. We index all the things. SQL, like select statements are faster now, but update, delete, and insert statements are much slower because we have many more data structures to be modified. But the other thing which is also important here is that indexes degrade over time. Maybe we added an index like half a year back that was helpful back then, but now because we changed our application logic, that index isn't used anymore and it's only decreasing the performance. How do we identify that? How do we see that when we talk about like continuous integration, CI/CD? How do we check that when we run things locally? We need to have this monitoring capability that will tell us, hey, this index that was useful half a year ago is not useful, not being used anymore. So it should be dropped. So those are the things that we have databases. And finally, the other issue we may have is bugs. So obviously, some of the bugs we may capture pretty easily with like unit tests, integration tests, but there are also bugs that are very like manifest themselves only because of the database engine we use. One of them is, for instance, Halloween problem. It takes its name because it was identified on Halloween. If you run a query like this, unpaid employees, and increase the salary of the employees by 10% for all the employees that earn less than 10,000, right? What can happen and what actually happened is that this query updated a row, increased the salary, and because the salary after the update, after the 10% increase was still below 10,000, the same entity was updated again and over again until finally all the entities, all the employees got 10,000, at least 10,000 of their salary. Right? This is the issue with your database engine, something that you may miss when you run things locally because database issues or engine issues are probably very edgy cases that are not very easy to be reproduced like in your testing environment. So generally, testing all that stuff is hard and we need to be aware of what may go wrong. But when talking about completely different area now, we typically interact with our databases using ORMs. ORMs, so object relational mappers, what they do is they allow us or they let us write a little bit of application code in JavaScript, Python, C#, whatever language of your choice is, and then they translate the query to a SQL statement behind the scenes. So let's take the example of n+1 select problem. Imagine that you have a table called aircrafts that have basically airplanes, and is in relation one-to-many with seats, basically because every aircraft may have multiple seats. So we would like to get all the aircrafts, and then for each aircraft, we would like to get like the number of seats it has, right? What may happen is this results in n+1 queries, because first query is for getting all the aircrafts from the database. And then for each aircraft, we send another query to get the seats from the table. So in total, we have one query for the aircrafts and n queries for every aircraft individually, which takes n+1 queries in total. Obviously, the more aircraft you have, the bigger the issue is. It can be solved by running one query to get all the data together with a simple join. However, how do we instruct our ORM to send one query instead of many queries? We need to go and change the something like global configuration of our ORM. Definitely something that is not near the application code we implement. So the moment we implement this application code, we don't see that there is an issue. And this global configuration may affect other things. For instance, the issue we have already seen. If I take the application code that like does this many joins and I want to go eagerly and join all the tables together at once, then we've already seen that this is an issue. So for some cases, we would like to run the join. For some other cases, we may want to run this in a lazily fashion. So basically to get this n+1 problem like purposefully. For some other things, we may even want to restructure the way we get the data. ORM is not a silver bullet. ORM hides the complexity behind the scenes, but does not solve our issues automatically. We need to peek behind the scenes what's going on and understand what is the implication of what we implement. The other thing we have is the so-called impedance mismatch. The impedance mismatch, which manifests themselves in like two different things. One idea is how do we represent object-oriented hierarchies in our ORM in our database? How do we basically get the polymorphism in place into our database? There are various solutions, various approaches like table per hierarchy, table per type, etc., etc. But now we need to ask ourselves a very important question. Should I start with defining my model in the application code? Or maybe should I start with the database and then structure my application code to resemble the data storage? None of these solutions is better than the other. Both of them have multiple issues. But generally, the outcome is if we make the wrong choices, then our model on whichever side is going to be inefficient, meaning that it's either the object-oriented model that we have that does not work well with object-oriented logic we want to run, or the database needs to do tons of work to represent all the object-oriented things we wanted to have in our language. So generally, no, it's not a silver bullet. There is no a simple solution that we could go because it all takes some pros and cons and we need to understand what we're doing. The other thing when it comes to impedance mismatch is data types. Simple as that. How do we represent a thing that is common in SQL engines? That is spatial data. Spatial data, so basically coordinates on the globe where something is, like GPS coordinates, right? Some ORMs will be able to represent that using native SQL data types. Some ORMs will need to serialize that to string or pair of numbers, right? Same goes for other things, for instance, binary data. But things get even more interesting when it comes to even strings. Like in databases, you have a thing that we typically call varchar, like variable character length. However, we also have a thing that is called collation. Collation defines the order of characters. For instance, it can dictate that when you compare two different strings, you should ignore the casing. And the uppercase character should be equal to the lowercase character, right? Or maybe the opposite, they should be treated differently. It can dictate which character is lower than which one. So for instance, you can change the order of your alphabet using collation, right? How do you do all of that with strings in the language of your choice? Can you change the implementation of string in I don't know, Java, JavaScript, Python? You can't. And because of that, you can't represent collation properly, and you need to do quite a lot of logic that like basically leaks between those two layers, between data layer and your OOP layer. Same goes for numbers. How do you specify decimals like numbers from database with different precision? We typically can go with like float or double in our language, but we can't specify exactly what the precision should be, but we can do that in the database engine. What this is gets even more tricky when we run heterogeneous ecosystem. So we have one data storage that is accessed by multiple applications written in different technologies, one of them being .NET, other of them being Go, yet another being Rust. How do we represent the same data in those various applications without hitting the impedance mismatch problem? This gets even more trickier when we increase the complexity of our system. ORMs pose even more challenges. I will just list some of them and briefly mention them. For instance, transaction isolation level. Do you know what your isolation level is, whether it's serializable or read committed? Do you know that in read committed, which is, by the way, the default for most of the databases, do you know that it is allowed to skip some row or get duplicates when you run select statement? This is perfectly fine according to the standard. Do you know who starts the transaction, who commits it, who rollbacks it, when does it terminate, and how? Do you know who controls the errors handling? What about caching, especially when you have multiple nodes running in your application? Do you cache data in the ORM, or maybe do you go to the database every single time? Do you create new connection? Do you have connection pooling? What do you do when you run in like Azure Functions or AWS Lambda? Who holds this connection pool, when it's by being like rolled, recycled, etc., etc.? What about query hints? How do you know whether you can specify the query hints? How do you even know whether the query hint is still usable and actually increases the performance? So ORMs, they also improve like or break things in migrations. What about databases? How do you know who controls tables in your database? Is it Flyway? Is it Liquibase? Or maybe it's your ORM? What if your ORM figures out that there is some like drift between your database and your application code? Is ORM going to fix that automatically? Some ORMs will do that, but do you want that? How do you roll back? How do you roll things forward? How do you keep compatibility? And more and more and more. Generally, ORMs are cool, but they scatter the configuration in so many places that it's very hard to understand what's going on. There are multiple moving pieces, multiple problems with like views, stored procedures, isolation levels, etc., etc. So ORMs, even though they are great, it's very hard to understand what they actually do without seeing everything behind the scenes. And that's the important part. We want to see everything that goes under the hood. We need to have the context and we need to understand everything to automatically troubleshoot and to find the root cause of all the stuff. So now let's see, how can we do things better nowadays using modern standards, modern approaches, and how can we do things that we call database guardrails to make sure that our things work well? The very first thing to understand is if we want to fix databases and deal with scaling databases and whatnot, we need to understand how they work behind the scenes. The very first thing that we typically get is the execution plan. Whenever you send a query to a database, this query goes through various stages handled by your database engine. First stage is parsing. Database engine parses the query text and creates something that we call abstract syntax tree, AST for short. Then this AST is being rewritten into some standardized form. Why? Because some queries are equivalent even though they have completely different like SQL text. For instance, you can use different aliases or different order of columns or whatever, but ultimately these things are equivalent behind the scenes. Then comes the third important part, which is called planning. There is a part in your SQL engine that is called planner that takes the query and tries to figure out, okay, how do I get the answer for the query I got? How do I find the data? And planning is a very sophisticated process of identifying what your data is, how to join tables, how to use indexes, which indexes to use and whatnot, basically to figure out how to do it in the most efficient way. And finally, the query is executed by the executor. So let's focus on the planning. What can we do with the plans? Whenever we send a query, for instance, in PostgreSQL, we can add the explain. And explain tells the engine, hey, do not execute this query but tell me how you would execute this query. And what we get in return is the execution plan. The execution plan is basically a big data explaining what's going on behind the scenes. It consists of things that we call nodes. Every node in this plan, more or less every node, is basically a node. And node can be of multiple types. For instance, node can represent an operation in the database. For instance, scanning the table, or scanning the index, or ordering things, or joining tables, or hashing, or other stuff that database needs to do in order to give you the answer. But the other thing that every node has is the cost. Cost is basically an arbitrary number that doesn't have any meaning when it comes to like either number of IO operations or whatnot, but it's basically a number that allows us to compare different execution plans, because the lower the cost is, the cheaper and the faster to execute the query is. So we want to find the plan that has the lowest possible cost. And cost is more or less correlated with the number of IO operations we execute. So how hard it is to bring the data from the drive to the SQL engine and process it. How many times we need to spill the data to the disk, how many times we can use caches, memory caches, or whatever. So this is basically how we get the cost. And the idea is that your SQL engine runs this, creates multiple plans, and calculates the cost for each plan, and then chooses the cheapest plan to execute the query. So this is how we could reason about whether our ORM code, or the code that, or the queries that ORM generated, whether it's going to work well, is going to scale well in the production, by looking at the execution plan. But how do we get the execution plan? And now the trick is we can use the OpenTelemetry. OpenTelemetry is basically a modern standard provided by CNCF, so Cloud Native Computing Foundation, that allows us to instrument our application on multiple layers like HTTP, ORM, SQL driver, whatever else, and extract things that we call signals, and those are logs, traces, and metrics. OpenTelemetry, OTEL for short, is basically a set of SDKs for various languages, C++, PHP, JavaScript, Python, Java, C#, whatever else, SDKs that allow you to get those signals from your application, so traces, metrics, logs, etc.
Let's quickly recap what I was covering. So OpenTelemetry allows us to basically, it's an SDK that gives us the ability to instrument our application on multiple layers. And we want to get signals, traces, metrics, logs, whatever else. The way it works is when we have a distributed system, what happens is we can control and trace how the requests are going throughout our system. Let's say that our user hits the node A, which is like load balancer, and then load balancer needs to call the application, needs to call the database and other nodes like behind the scenes, okay? What happens is this whole operation of calling all of that is basically called a trace, and a trace represents some workflow that was executed in time. And the interaction between the nodes is called span. So we can get span for every operation that was happening behind the scenes. And we can get human-friendly details of what was going on, the name, timestamps, etc., etc. So this is how we run observability and monitoring today, in today's modern world. Now, how can we use both of these things, the execution plans of SQL query and the OpenTelemetry spans, to tell confidently whether our application is going to work well in production? Well, we could run load tests. We could run big load tests on our application, see how things perform, what they do behind the scenes, get the OpenTelemetry spans, and reason on that. But the problem is, load testings are very late in the pipeline. Very late, meaning that we need to run them only after we're done with implementing our application code. And we can't wait for that. We can't wait for load tests to identify issues and to learn that our application is not going to work well. Load tests are slow, expensive, and way too late in the pipeline. We need to push things to the left and do them as early as possible. And how can we do that? Metis comes to the rescue. So Metis is basically a software as a service that uses OpenTelemetry and uses execution plans from the database to give us this fancy experience of identifying everything that happens and whether it's going to scale well or not. So it gives source code integration, pull request analysis, and other things. So let's see a very quick demo of what's going on. So when you integrate your application with Metis, which takes basically OpenTelemetry that you already have in your applications nowadays, what you can get is you can get a tracing of everything that happens like in your test, during your implementation or whatnot. And this tracing gives us something like this, for instance, that, hey, our application exposes this REST endpoint. When someone called it, they got HTTP 200 in response. But more importantly, those are the SQL statements that were triggered against the database. If we want to understand those SQL statements, then sure, we can get the SQL, like a SQL statement text. We can get some metrics. We can get visualization of the query to see all the details of what was going on, what was the cost, etc. But most importantly, for us developers, we get automated insights telling us, hey, this thingy is not going to work well in production. There is some critical issue here. And this is the impact of this query. And this is how we fix this query, how we make it better. So we get automated insight right at our hands just when we are implementing the application. So this is all we get when we drop one dependency to our product, to our app, and we integrate OpenTelemetry. But that's not the end of the story. What we can also get is we can, for instance, integrate that with CI/CD. For instance, we integrate that with GitHub Actions, and what happens is whenever we have a pull request, we can, for instance, automatically analyze the queries coming from that pull request. So now when you do the diff, when you review the code someone else wrote, you can see not only the changes in application code, but also how it actually performs in the production. The other thing that comes is how do we take all of that from local and give the observability for the production environment. So we run a very tiny open source Docker alongside our production database. And for instance, we get automated analysis of our database. For instance, telling us that, hey, there is a table that is called booking flights that has like critical issues because it doesn't have indexes on it, right? Or the other thing is you may get observability dashboard with all the details of what's going on, how it's running behind the scenes, like the slowest queries, extensions, etc., etc. But more importantly, for instance, hey, you have indexes on your database configured, but it seems like this index hasn't been used for the last 2 weeks. So we can immediately see how your performance degraded over time. And the important part is Metis doesn't want to put you like or show you metrics, CPU spiked or memory increased. No, Metis doesn't expect you to put thresholds on the stuff. Metis tells you exactly what you need to do, how to do that, and in the future even submit an automated pull request to your code base, for instance, to modify your ORM configuration to increase the performance. So this is the idea that we get, right? And we get all of that just by using open standards like OpenTelemetry and open source solution. So coming back to the slides, Metis integrates with your code, whatever language you use, whatever database you have, whatever ORM, HTTP server, etc. you have. So to instrument the application and get the OpenTelemetry traces and spans and execution plans from the database to tell you whether things are going to scale well in your production. It integrates with your CI/CD pipeline so that it covers you when you just implement the code, and when the pull request is created, it can immediately tell you that, hey, this thing is not going to scale well in production. You don't need to wait for the load tests to be executed or even for the deployment just to see that, hey, this thing is not going to work well. It gives you full observability of everything you have, like your database, your performance. You can use it with CLI tools, you can use it with ad hoc queries, etc., etc., and it protects your database from breaking, from bugs, from ORM issues that we have, and from load tests that are very expensive, very heavy, and run way too late. Metis covers all of you need to make sure that you have proper database guardrails in your CI/CD pipeline, and that you can run all of that as early as possible and push to the left. So being all of that said, I would like to thank you for listening to this talk, and now it starts the Q&A session. So if you do have any questions, I'm happy to take them and answer.
Thanks a lot, Adam. That was really interesting. I really like the energy you were presented your lecture in. And I can see that there are some of interesting questions, and let's pick up the most interesting ones and try to answer them.
Okay, so let's go from top to bottom.
Thank you, Adam. So let's maybe answer for the first questions. What are some common mistakes or pitfalls to avoid when implementing CI/CD, and how can they be avoided? Maybe related to the database that you're talking about.
Yeah, and the most important part from my experience when it comes to CI/CD is that we test stuff using mocks and not in the infrastructure we are dealing with. So the problem is when you run things locally and run all the tests, unit tests, integration tests, whatever, and you use database that you think is the proper one, but it's like H2 in memory database, then you're not running the stuff you want to run. Because later on you deploy the stuff to production and then you have like Oracle database, completely different license, completely different configuration. So your CI/CD and basically your process tells you that, hey, all is good. But when you go to production, then you realize that because of some quirks of different infrastructure, you get completely different results. So the biggest issue I would point is not using the same components locally as you run in production. You can fix that, or you can help that a little bit by using infrastructure as code and by running basically the same environment, using the same like cloud components, the same license, etc., etc. But generally, this is pretty often hard thing because you may not have money or not be allowed to run database with the same license as you run in production, right? You may not even have the access to the same hardware, right? What if you run on an IoT device that you just can't run locally, right? So all those things, I'm not saying that it's simple to be solved. It's not. And actually, I have a different talk you can find on YouTube how to actually do testing with those conditions, under those conditions. But generally, whenever you run load tests or whenever you run CI/CD in your pipeline, strive for having exactly the same environment. Otherwise, you'll run into weird issues later on.
Yeah. Thank you for this answer. The second question is, why is Metis better than native database optimization tools?
That is a fantastic question. Native database optimization tools, they have two issues, or they do not cover two things that Metis does. First thing is they are very database centric, meaning that they do not know what your process is. They do not know when you were deploying stuff. They do not know what libraries you use or what configuration of caching you have around, right? They are great when it comes to improving, like tuning your index or suggesting your index, but they do not know everything around. That's the very first thing. Second thing, those things, those tools, they pretty often give you the numbers based on the characteristic of like performance you observe. So they give you, hey, this is the CPU spike, this is the IO spike, memory spike, but you do not understand whether this memory spike is because of you have wrong configuration in your ORM, your application, or maybe in your auto vacuum in database, right? You need to have this holistic approach to connect all the dots together. So we are not trying to necessarily replace the tools of your database. They are cool and they solve very specific use cases. However, they do not give you the broad context of everything around. And Metis does you exactly that. It gives you those automated insights that take into consideration multiple things of your CI/CD, application characteristic, language you have, and the database you use. So they are better in the sense that you do not need to come up with thresholds based on the metrics you get from database, but you get actual solutions that you can just apply and you are sure they will work well.
Yeah, great. Thank you. And I think the last one question maybe, is Metis only for SQL database, or does it work with, or it works with the MongoDB, for example, or other databases?
That is a fantastic question. At this point, production support is for Postgres and MySQL. We are working on supporting MongoDB and other NoSQL, mostly document databases initially, pretty soon. So our roadmap says that this should be done, let's say 2-3 months. and then document databases will be supported. Mongo will be the very first one to support. Later on, Elasticsearch as well, and other databases of different characteristics. This also is going to be available later this year.
Great. So we have 4 minutes left. Let me ask you one more question.
Sure.
Why should we anonymize logs? What security concerns should we have in mind?
That is a very, very good question. And there are a couple answers to that. First answer is, well, you have law. You have GDPR, you have HIPAA, you have California Protection Act, you have other legislations that basically disallow running or processing data in non-production environments. So, or actually they do not disallow, but what they do is they impose tons of limitations, how you can do that, who can do that, whether it's controlled, how can we remove the data as customers and whatnot. So generally, we want to anonymize the data when taking them from production to staging, just to not need to deal with this data, with information security, with red data as it's called in some components and whatnot. So this is the very first thing. Second thing is just security. Let's face it, developer environments and non-production environments are much less protected when it comes to security and access. We know all of that. We put IAM role with access for everyone on the team to call any API in our cloud, right? If you put production data in non-production environment, you just basically ask yourself for troubles. It will be a problem that someone just takes this data and even involuntarily, but leaks it somewhere, takes a backup, puts it on some storage that is publicly exposed because we didn't secure the configuration and whatnot. So another thing is security. We just want to be careful not to put data in developer environments. And third thing is to control how we locate the data or how we store it. It's much better if we just don't have the production data locally. Why? Because then this data leaks to multiple places, to SQL database, to backup storage, to log files, to, I don't know, APIs, to screenshots, to internal Jira system or whatever. And you just see someone social security number being exposed in one of those systems. So it's much harder to do this data governance where the data is stored. It's much harder to be done when we allow for the production data to basically roam around. We would like to control that, and to do that, let's just anonymize all that stuff just to be safe and secure.
Yeah, thank you. I think we should finish. Thank you. Could you please choose the best question?
Yeah, best question. I think the best question, let's take first from the top. What are some common mistakes or pitfalls? That was actually the best question because the answer is super long. So let's pick that one.
Okay. Thank you, Adam. Thank you for sharing your thoughts with us. And we will continue.